Okay, so this is part 2 of linear stability analysis, and what we're going to look at is iterative maps. So in this case, we have a system where the next value of our variable x, xn plus 1, is given by some function of x, or some function of the previous value xn. So here, where previously we were looking at a differential equation where time is continuous, in this case, time moves forward in discrete steps. Now, we can still have stable points, but in this case, a stable point, x star, is where f of x star equals x star. If we put x star into our function, we get the same number coming out the other side. And again, we're going to now consider a point close to, that's not a stable point, that's a fixed point. I made a mistake there. Let's just see if I can rub that out. So this is a fixed point. So what we need to consider is point that starts at x star plus epsilon, where epsilon is a small number, but I'm calling it epsilon I because we're moving forward in steps. Clear it as an I. And so, well, I'm actually going to use n, but if we have x star plus epsilon n plus 1, we can find the value because it's equal to f of x star plus epsilon n. So that's exactly as our equation above, but it's just substituting x n plus 1 for x star plus epsilon n plus 1. Okay, so we now do a very similar sort of Taylor series, and that's equal to f of x star plus epsilon n f primed of x star plus epsilon n squared terms and higher terms. And now the left hand side is still x star plus epsilon n plus 1. Now f of x star, that's just equal to x star from our relationship here. So that's x star plus epsilon n f primed of x star. And now what we can say again is that this term of epsilon n squared is approximately equal to 0 because epsilon is small. So that's all we have. But now what we can do is cancel out x star, which we have on both sides. So what we're left with is epsilon n plus 1 is equal to f primed of x star times epsilon n. And something to be aware of here is that this term here looks a bit horrendous, but it's just a number. It's just the gradient of the function at the stable point. And we can say in general, epsilon n will be whatever value we start with, epsilon naught, multiplied by the gradient of the function at x star to the power of n. Now, so clearly the stability again is going to depend on this term here. It's slightly different to what we saw with the differential equation on the other side. Now what matters is if the modulus of the gradient x star, if that is less than 1, then the bigger n gets, then as n goes to infinity, epsilon n will go to 0. If, on the other hand, the modulus of the gradient at x star is greater than 1, as n goes to infinity, epsilon n goes to infinity. Now, of course, it won't, well, probably won't go to infinity. It may not go to infinity because we've made lots of assumptions about epsilon being small and they'll all be broken. But we'll know that it will definitely move away from our point. So we can say here that here we have a stable fixed point and here we are unstable. Now again, we've got the case of, there's also the case of what happens if the gradient is equal to 1, and we'll look at that in a moment. First of all, what I want to do is introduce the, let's go to a different colour, the Lyapunov constant. And what we look at is an average of the natural log of the function of x star, or the gradient of the derivative function of x star, where n is a large number. And we might call this constant, let's call it lambda. Now, so this is a nice quantitative measure of stability. Now here we need to notice that in this case, the log of the gradient at x star, if it's less than 1, then it's going to be is negative. And here, the log, if the number is greater than 1, is positive. And so we can say for lambda is less than 0, it's stable. For lambda is greater than 0, it's unstable, or maybe even chaotic. Now, a couple of other points to make. If the gradient at x star is 0, then lambda will be minus infinity, and this is super stable. Finally, coming back to the case where this gradient is 1, if that equals 1, then we don't know if it's stable or unstable. And indeed, the Lyapunov constant will equal 0. It's not positive or negative. And in that case, what will happen will depend on terms of epsilon squared and above. Okay? Right. A final thing to mention is that if we just have a quick look again at this equation here, which was the long-term equation for epsilon n, where it's your original epsilon multiplied by f prime of x to the power of n, then if we imagine taking the log of both sides, then this this part here, we get the sum of the logs. And so this is really why when we're taking an average here for the Lyapunov constant, we want to take a sum of the logs. Okay. So that is a way of looking quantitatively at the stability of a function in an iterative map where time is discrete. It's quite there are similarities with what we're looking about in the differential equation above. Okay.